Okay, today we will continue our discussions on asymmetrical induction machines. So, basically we are trying to extend the principles of rotating field theory and symmetrical component theory for practical cases of asymmetry which we encounter. Okay. And we have seen that these are the two powerful tools. One is the rotating field theory, where we define rotating field impedances, and instantaneous symmetrical component theory, symmetrical component theory, where we write the equation in terms of the positive, negative and 0 sequence voltages and the sequence impedances. Okay. Now, we have been referring the topic or dealing with the topic using some of the published literature, which is primarily some of the research papers in journals. Okay. So, the rotating field theory, the reference is from J. E. Brown and C. S. Jha. This is Proceedings IEEE, volume 109, part A, number 43, February 1962. This is one of the world classical papers, pages from 59 to 69. So, this is the paper where we discussed with the generalized rotating field theory. Okay, so, since I have dealt with this earlier lectures centered around this paper, I advise you to get hold of this paper, read it in, and then my lecture would be a complement to what you read. Okay. So, that will be helpful, I feel, and this is only constraint that this paper had was, it is rotor was always squirrel cage or symmetrical. This was the constraint. Any type of stator configuration, any type of disposition of the stator winding, any number of stator windings, it will take care of, okay, in the rotating field equations, where we can write down, we can calculate the currents for the given set of voltages and also the torque. Okay. So, we have to calculate the torque as, which is the total air gap power divided by synchronous speed for different fields. Whatever power you feed to different fields, that will give up the respective torques. Okay. Now, in the last lecture we also took one practical case, it is a 3-phase motor with single phase supply. Okay. And this aspect is also dealt with in one of the papers. There are a few authors. This has appeared in IEEE transaction on power apparatus systems, because this was presented in the IEEE winter meeting in 1982 in New York. Power Engineering Society winter meeting. This was presented in New York. Incidentally, I was the person who presented this paper in New York AS meeting, and it subsequently it appeared in the IEEE transactions later. It appeared in 1983 on that. So, this is about this deals with the it is a transient analysis of 3 phase induction motor with single phase supply. So, it deals with transient analysis, but steady state what I have dealt with is one part. I have deliberately avoided transient because it involves much more modeling. You have to do a modeling of the machine with single phase supplies. That is also explained in the paper incidentally, but you can read this paper. Is it okay? You have a reference here. Now, what we have in the last class, we said that it is possible if a 3 phase say delta connected machine is there, and if you one line is disconnected, you can supply a voltage, it will carry a current I here, and it will carry the, this will be ISA, this will be ISB, and this will be ISC, and these are the voltages VSA, VSB and VSC, okay. And this was the capacitor that you connect, right, which can have a reactance XC, right, or minus JXC to be specific, right. And you can write down the boundary conditions or equations. You can write one equations okay. You can write one equation here, and maybe you can write maybe another equation here or whatever it is, okay, right. And what are the equations that you get? One will be V minus VSI is 0, isn't it, for this loop V, if you take this V minus VSI is 0, okay, that is one equation, and other equation is VSC minus JXC into ISC minus ISB is 0. Let us see whether that is correct. So, VSC is here, if you take this loop, so it will be VSC minus this current. What is this current here? What is this current will be? ISB, this is ISB, this is, so it will be minus JXC into ISB minus ISC is 0. I think that is what you have written, okay. ISC minus ISB, is it correct or wrong? What is the, you see, this is minus J, this is VSC, what is this current? ISB so see, if this is ISB and this is ISC, this will be ISB minus ISC. So, you check whether what we have written is correct, okay. Now, we take this loop, this is the VSC, because this direction is correct, VSC minus this loop, okay. I think, but then I think because this is minus JXC, where it is not, I think it is ISC minus, I think this is correct, I think ISC minus ISB is 0, that is correct actually, ISC minus ISB, okay, because we have put a minus JXC here, right, okay. So, that is correct. So, this both the equations are correct, okay. Now, what you do, we took a symmetrical components on this, well, we know symmetrical component what is VSA, VSB, VSC, because we write VSA is equal to V1 plus V2 plus V0. Anyway, V0 is 0 because there is no 0 sequence, and VSB will be A square V1 plus A V2, is not it, etcetera. So, you substitute for VSC, and similarly for you write what is ISA, ISB, ISB, ISC. So, what we get what is V1 and V2 in terms of V, that means at each speed and capacitance there is a particular value of V1 and V2. So, they a 3 phase machine operating on single phase equivalent to 2 machines, one with V1 another with V2, okay, and the net effect is the sum of these two. Okay. So, is as if you are applying one positive sequence voltage V1 and then positive sequence voltage V1, negative sequence V2. Is it clear to you fundamentally? So, a 3 phase motor with single phase supply is equivalent to cumulative effect of the same motor applied with V1 one time and V2 and take a superposition of these two. Okay. You are giving a positive sequence voltage, negative sequence voltage. So, it will give you a V1 will give you I1 and V2 will give you I2, because we know V1 equal to I1 Z1, V2 equal to I2 Z2, you know Z1 Z2, and they are all speed dependent. Okay. Then we want to have minimum value of negative sequence voltage, isn't it? If that is also predominant, it will give rise to lot of noise and vibrations. Therefore, the unbalance is the factor is defined as the magnitude of V2 divided by magnitude of V1. So, we get a term for this. Unbalanced factor is now does not depend upon V. What does it depend upon? It depend upon capacitance, it depend upon Y1 and Y2. What is Y1, Y2 is positive sequence admittance and negative sequence admittance, which is a speed dependent term. Therefore, unbalanced factor will be depend upon the capacitor connected and the speed in which you are running. So, for the same capacitance, unbalanced factor will not be same. Okay. Is it clear? If you connect take a 3 phase motor, connect single phase, and that capacitor will give you a given unbalanced factor which depends upon speed. Okay. At starting it may give you one unbalanced factor, running it may give you another unbalanced factor. So, what is your purpose is to minimize this, you know, if this unbalanced factor we define like this, which is a function of xc and y1 y2. Okay. This is actually magnitude, because this one was a vector, this one was vector, okay, y1 y2. So, if you write in terms of the magnitudes, okay, you have this k1 k2 etc., and you want to minimize this unbalance, at every speed. So, there is one particular values of xc at every speed which gives you a minimum unbalance, is not it. So, at every speed there is one particular xc which will give you minimum unbalance, because that is the most appropriate value of capacitor to be connected at that speed. But unfortunately, that xc is not same for all the speeds. Okay. Therefore, we have to solve an equation, right, and then find the these constants, okay, and in solving this we find the value of capacitance at different speeds. So, what you require is a varying capacitor, continuously varying capacitor. So, start you require one capacitor, run you require another capacitor, okay, right. So, you generally we discovered that the variation of capacitor xc will become with speed will be like this, which would also mean that you may have a, this is C and this is xc. Okay. So, you will require high capacitance start which run for a short time, then you have another low capacitance that run, supposing this is some speed in which you are running, okay, some points, right. So, now you can calculate the value of capacitance. Is it okay? At least I hope you are clear of the problem and clear of the solution now. If you are given an induction motor, knowing its parameter, knowing its Z1, Z2 at different speeds, you can find out value of capacitance to be connected to have a minimum unbalance through this procedure. Okay. This is a very practical way of doing it. Okay. Then we take also a star connected system, that was a delta connected arrangement, this is a star connected arrangement, where this will be the current, input current I and input voltage V. Okay. Then again it will have the currents ISA, ISB, ISC. Now, you must be very particular about direction of these currents, because as the motoring all the currents will be going into the windings, right. What will be the direction of voltages? Huh? What will be the direction of voltages? Where I should put? Put arrow top or bottom? Top. So, that is important, because this will be VSA. Okay, you arrow top. So, this is where it is entering the current is. If it is generating, this current direction will reverse as the voltage, and similarly you write VSB and you write VSC, and this will be minus JXC. Okay. And then what will be, suppose what will be the maybe what is this current here, say what will be this current? I minus ISA, what is I? ISC, is I ISC, I is minus? So, this will be I I minus IS A, I is minus ISC, you say, this will be the current. Okay. This is the current going out like this, okay. And you can write again, pardon, oh ISB, sorry, minus I, this is same, you know, I is, so you discover that if this is, if at this juncture of course ISA plus ISB plus ISC is 0, I naught is 0, V naught is 0. Okay. If you take this loop, this I is going like this, and so I equal to minus ISB, is it right? Is it okay? And so you can write down, say for example, one loop equation here, that will be V minus, what will be this, the loop equation will be, what is this loop equation? Voltage KVL basically, V minus VSA, what will it give you? V minus VSA, then plus VSB equal to 0. Is it right for this loop equation, say 1, right? And if you want to have this loop equation, then you have VSA minus, so this will be VSA minus of this is because it will be coming like this. So, this is minus JXC, minus of minus JXC into the current, that is minus ISB minus ISA. This is VSA, and then sorry, minus VSC, no, this is VSA, and then you go down, minus VSB, VSC is 0. Am I right? I am just trying to, it is not a big deal honestly. You have to write these two loop equations, and then you have to solve for this. Okay. Okay. Now, you write the two, so basically what you do is, write the two loop equations, right, then solve for V1, V2. So, you can again have to find an expression for the positive and negative sequence voltages using the symmetrical component concepts. Is it okay? So, this is the expression that you will get V 1 V 2 as written here. Okay. So, you have to derive this. All those who did not do this, in fact, some have given already assignments for delta connection. Those who have not done that, they should do it for star connection now. Okay. Right? I'll give you by before the next class you bring it others, right, because I have got 7 people, I have the assignments. So, others also should be doing this. Please, it is not it appears straightforward, but it is necessary for you to get there. So, what you observe here is this V 1 V 2 is now a function of the applied voltage V and the capacitor X C and the impedances Y 2 and Y 1, is not it. So, they are Y 2 Y 1 again will be depend upon the speed in which it is running, right. You know the equivalent circuit for Y 1 Y 2, it is nothing but 1 over Z 1 and 1 over Z 2, is it okay? Okay. Now, so you are now able to estimate the positive negative voltages V 1 V 2, then the same in 3 phase will be applied to the same motor, okay, and then you estimate the performance, okay, and you do repeat, that means you can also find out the unbalance factor which will not depend upon the V. So, it will depend upon the capacitance Y 1 Y 2, okay. Unbalance factor which is defined as the magnitude of V 2 divided by magnitude of V 1. We know the expression of V 1 V 2 in a phasor form, take its magnitude and that will be, because its magnitude you have to take a real imaginary part and take its magnitude as usual, okay, square root of real part and square plus imaginary part square. So, you have an expression like this which again depends upon capacitance Y 1 Y 2, okay. So, you have to find out the capacitance to give minimum unbalance at a given speed, is it similar even on star connection, is it okay? At a given speed you have a motor, you have a capacitor run at some speed and then you do not want it to have a too much of negative sequence. So, you get another equation for a quadratic equation you will get, okay, right, and where C 1, C 5, C 6 are the constants which are again functions of the admittances, okay. So, you have a quadratic equation in X C. So, solve for X C. So, you can find the value of capacitance for star connection also for the given motor at a given speed, okay, right. So, again it will you may also have a similar curve of variation like this X C versus speed, okay, and some C versus speed, this will be X C, okay. So, you can estimate through a simple computer program, the value of capacitance versus speed, okay. When once you do that, then next step would be you can easily calculate the performance, because your motor will now be supplied with V 1 and also with V 2, is not it. What it means is you are supplying both V 1 and V 2, okay, and then it will result in I 1 I 2 and it will result in T 1 T 2, which you can estimate for the given V1 V2 at a given speed. Is it okay? So, the net current will be, torque will be T1 minus T2 and the current would be I1 plus I2, whatever in the cumulative effect, you can say sum of these two, each of the windings, I naught is 0. So, you can estimate the steady state performance of a 3-phase motor with single phase supply with the given capacitance and speed. Okay. So, I think it is a you can, some of you can take it as a project. Right. So, you can say develop a MATLAB program to estimate performance of 3-phase star and delta motor, okay, for different speeds at suitable XC, suitable C or XC. Suitable C means you have to estimate which is the one which gives you the minimum, but again you should again it will vary, is not it. So, you can take some any machine parameter which are, in fact you can even take up what is given in this paper also and try to get this performance, it will be interesting, okay, and then compare with normal performance. Right. This is one of your group can take up this project. Is it clear to you? Any doubt on this? So, you have to develop a program, that means you have to, what is the data you will feed to your program? Parameters of the motor, number 1. Okay. Then after finding the parameters of the motor, you find out Z1, Z2, Y1, Y2 for different speed. So, your iteration first will be you take speed equal to speed 1, you have to vary from speed from 0 to 1 per unit speed. Okay. Then you calculate Z1, Z2, right. Then you calculate XC for minimum unbalance, right, and then choose that XC at that speed. You can estimate. Suppose the ideal situation is you have a variable XC, say, then at that XC what will be the best performance, or you can take a fixed XC, starting one XC, keep it for some time, then you see like you can think of a 2 value capacitor, bacha capacitor, bada capacitor, okay. You can think of starting one and running one, you can't continuously vary, you can't have variac, a farmer cannot have variac in his farm, okay. So, that is another thing, okay. Think of this, I think it will be one interesting small project for you to do, okay. Then you can also see what is the star and delta, which one you would use, okay. Now, most of the pump motors used in India, they are all delta connected incidentally. Why? Why are they delta connected? Do you know the reason why most of the motors are delta connected while most of the generators are star connected? Motors are delta connected, why? Any reason? Not clear. How are they started? So, you need a star delta. This is because for star delta starting, star delta means initially it must be star and then become delta. So, starting we need a delta motor, is not it. Okay. But if a motor is delta connected, okay, this is okay, this is a 415 volts 3 phase 50 hertz supply. Okay. Can it work on single phase? You can connect a capacitor, but if it can work on single phase if the 3 phase one line is disconnected. Okay. But if you have a 230 volt supply, will it work? Okay, I take a normal motor, delta connected motor, go to your house. In your house, I want to run it as a pump. Is it possible? The normal single phase supply is what voltage? Single phase supply is 230 volts, isn't it? 230 or 240 volts. Obviously, this arrangement may be okay if your one line goes off as it is. Okay. And the other, if you have a star connected machine, again it will be 415 volts, and you can still connect a capacitor here and run it. So, then it will be running at 415 volts single phase, when one of the lines is disconnected, you can still operate. Okay. But if you want a motor to be available for 230 volts, what do? You want to take one of the available motors. Okay. So, you have to, what you should do? One way is ask the fellow making the motors to rewind it or whatever it is. Otherwise, this one, if it is star connected machine, the same thing you can connect in delta. This star connected machine connect in delta, what will be the voltage, rated voltage here? 230, is not it? Because each of the phase voltage will be 230, right? Is it clear? So, one practical way is you buy a star connected motor and connect in delta, run it as single phase. Okay. So, that means buy a star connected motor and connect in delta and run on single phase supply. This is the only practical way. If somebody, otherwise you have to have make a separate single phase motor, which again more expensive, etc. But this may be more, this is considered as one of the options, okay, because you can't build large motors, say 5 to 10 HP in single phase mode. Single phase motors are limited to fractional horsepower. Okay. So, this is what you will understand. Is it okay? Right. So, I think we have covered almost all possible practical cases with rotor symmetrical. Till now, we were happy the rotor was symmetrical. Now, next thing is, suppose the rotor also become asymmetrical. For some reason, rotor may become asymmetrical willingly or unwillingly. You have a nice squirrel cage bar, maybe one bar get disconnected, or you have a slip ring winding where you connect the rotor windings in asymmetrical fashion, but it is often being done. Okay. Or a rotor, you connect some converters and only 2 of the 3 windings are operating at a time. Okay. If you connect some converters. Okay. So, next we have to look at a case of rotor asymmetry also. Okay. So, we take up that now. So, again we can extend the rotating field theory, generalized rotating field theory of a, now the rotor asymmetrical is invariably, let us take a wound rotor machine. Though squirrel cage asymmetry is less option, except there is an accident of disconnected bars or like that. Let us take asymmetrical rotor winding wound rotor induction machine, wound rotor induction machine having asymmetry in stator and rotor windings. So, I have both asymmetry in stator. Let us take this. This is our next analysis, maybe then we would have completed all possible asymmetries. So, you should be then you are able to now analyze any type of special machine or special configuration of induction machines. Okay. Now, this has been dealt with in one of our old papers. I will give you a reference, because I will go systematically from this paper, so that you can read it. This is authors are C.S. Jha and S.S. Murthy. This is in Proceedings IEEE, volume 120, number 8, August 1973, pp 867 to 873. This is rated as one of the very classical papers. Of course, this has been appeared in many books also. In fact, this paper has been referred in a recent book by M.G. Say on, he has referred to this paper. Okay. Book. If you look at the recent book by M.G. Say, which appeared in the last few years, 4 5, it refers to this paper. This is perhaps the only paper which deals comprehensively on asymmetry in stator and rotor. Okay. So, what we do is, I will try to take you through a tough path now. Okay. Starting from some simple, let us assume there is only one winding in stator, okay, let us say winding 1 or something, and there is another winding in the rotor, winding 2, which is short circuited. Okay, that is very simple. So, and then you apply a voltage, fixed frequency voltage V, and it carries a current, say I1 or something, say V1, right, and let the rotor be rotating at a speed omega r electrical radians per second. Is it clear? I take one winding stator, one winding rotor, I short circuit the rotor, I rotate it. Okay. So, in fact, if you want to write it in a another mode, you can say I have a winding here in the stator and is carrying a current I, and I may have another winding in the rotor okay, and maybe this is I1 and this is carrying a current I2, but this winding is short circuited, rotor is short circuited, okay, but rotating at omega r. Okay. Let us see what happens. So, the stator carries a sinusoidal current due to sinusoidal voltage, and then it will let us see what are the type of fields it will produce, okay, because this is producing sinusoidal current means what it will produce, this winding, it is having a pulsating field again, is not it, pulsating field. So, it will nicely produce a field which rotates this plus omega and another minus omega, is not it. Two rotating fields it will produce in the air gap, okay, and that will in turn will induce a voltage, these two fields will induce a voltage in the windings which will oppose. Now, that will induce a current in the rotor also, okay. And what current it will produce, what frequency, you should be clear, okay. It will induce, because if it was just standing like this, it will induce the same as the supply frequency if it is held stationary. If the rotor is stationary, it is like a transformer, is not it? It is like a transformer. So, it will have the same thing. Okay. Now, that means I have a single phase, single winding stator and a single winding rotor which is shorted. So, a single phase winding on the stator supplied at a fundamental frequency f, which is omega by 2 pi hertz, no problem. It is running at 50 hertz or normal line frequency. Now, it carries a current, okay, which produces an MMF which act on the and which produces a flux, right, is not it? I think what we are telling is very rudimentary, okay. And then this flux will have a what this, there will also be, it will also produce a leakage flux and both forward and backward rotating fluxes, that we already are aware of, okay. Both forward fields will be there, backward fields will be there, and we normally write the impedance will be that winding resistance, that winding leakage reactance, okay, leakage fluxes, and there will be forward, fundamental forward field will induce a voltage in its own winding, we call it as proportional to x1f. So, x1f is the self reactance due to forward field and x1b is a reactance due to backward field, and we define it as whatever is the voltage induced in its own winding divided by its own current, we define it as the reactance, okay, like self reactance. Then there will also be the reactances due to all the harmonic fields 2 to, okay, there are n harmonic fields, it is okay. So, harmonic fields are also there, but we know that harmonic fields will be in a wound rotor machines, they do not produce torque because it cannot react to the rotor, because they are of different poles, okay. Therefore, normally what you do is all these harmonic fields, the fluxes due to harmonic fields you just combine with the leakage flux only. So, it is considered as an additional leakage flux, okay. This is generally done in the wound rotor machines. In fact, you must be able to answer this fundamental concept, you should know. Difference between a squirrel cage machine and a slip ring machine is the squirrel cage machine is capable of reacting to different number of poles, therefore, you know even the leakage reactance values will change, okay. So, with this we can write that the primary impedance or the stator impedance Z1, I can write it as its resistance and this reactance X1, which includes all the harmonic fluxes, and one forward self reactance and backward self reactance. Is it clear at this stage? You have forward field and backward field, fundamental only, we say fundamental forward field and fundamental backward field which will induce voltage in them. So, this X1 is its own basic leakage plus harmonic fluxes, these are harmonic fluxes, okay, because these are all harmonic fluxes. Because in the air gap, whenever there are harmonic fields, it will also produce some fluxes. So, they get combined, okay. Now, the R1 represents the effect of power loss due to leakage and harmonic flux. So, R1 is a resistive component which will include any stray losses etc. We can include everything, and X1F, X1B are the self reactances due to forward and backward fields. Okay. We are repeating the same thing. Now, similarly for rotor, right, rotor also will have Z2 will have its own resistance R2, leakage reactance which include all harmonic fields, and its reactance is X2F and X2B. Because if you pass a current through the rotor of any fundamental frequency, you hold it, so it will also produce its own forward backward field, induce its own induced voltages. Okay. Right. So, after all these impedances in a circuit is represented because they reflect certain voltages when a current is passed through them, right. Okay. Now, the forward and backward fields produced by the stator current, forward backward produced stator current, what will it do? It will, because it is a fundamental frequency f, it will give rise to, they rotate at two fields, plus omega electrical radians per second and minus omega electrical radians per second. Okay. So, it will have plus omega is forward field, minus omega is backward field with reference to stator. Okay. Then what will happen? This forward field will induce a current in the rotor and backward field will also induce a current in the rotor, is not it? Forward field, after all rotor is the short circuited rotor, and forward field will produce a induce a current at F minus Fr, because rotor is rotating at omega r electrical radians per second, where Fr is omega r by 2 pi. Okay. So, rotor gets two frequencies induced, though the stator has only one frequency f, another is f plus Fr. So, forward field will produce in a normal 3 phase normal single phase motor, that is what we have seen, rotor will have two frequencies SF and 2 minus SF, you are aware of this. Okay. So, rotor now will have two currents of two frequencies. Okay. Any doubt on this? Clear? Okay, let us go to the next step. So, Fr is omega r by 2 pi, right, omega r is the rotor speed at electrical radians per second. Okay. Now, each of these currents in the rotor winding produce its own forward and backward fields, is not it? It is a single phase winding. Okay. Now, how many forward field will be there, how many backward field will be there? There is one current F minus Fr, another current F plus Fr, is not it? There are two currents in its own single phase winding, and this will produce one forward field and one backward field, this will produce one forward field and another backward field, is not it? Huh? So, it becomes more, right, is it clear? Because rotor is unbalanced, rotor is only single phase, it is not, okay, it will give a forward field and a backward field. Okay. So, the two backward fields have in space of minus omega plus or minus 2 omega r, and which will induce currents of frequency F plus Fr in the stator winding. Now, what will happen is those fields will also induce another current in the stator winding. Okay. I am just trying chain reactions which will be there. Okay. So, the frequency F plus Fr current will be there in the stator winding, and the other winding will be in phase with the inducing field. See, there is one is a inducing field, other induced field. Whatever is inducing field will be at synchronism with the one, but the backward field is the one which is creating additional currents. Okay. Right. So, these in turn produce forward and backward fields, and forward field is stationary with respect to inducing fields. Okay. Rotor one field is a rotor forward field will not produce any other frequency, it will be at the same frequency as the stator. So, one will be stator will have f and f plus fr etc. And the backward field produces another series of fields. So, there will be one more current coming back into the stator winding, mirror reflection. Okay. Therefore, what you observe is in the stator first f you have applied, then you will have f plus or minus 2 fr, then f plus or minus 4 fr etc. Same you continue, and that means you have f plus or minus k fr where k is an even integer. This is what you will have. Okay. So, you tell f plus or minus 2 fr, f plus or minus 4 fr, these are the new currents which will be induced, because for inducing field the stator winding is like short circuited except for the fundamental field, except fundamental only there is applied voltage. Yeah. Okay. So, but the similarly for rotor has frequencies f plus or minus fr, f plus or minus 3 fr and f plus or minus k fr, where k is odd, right. So, the f will produce f plus or f stator will give rise to f plus or minus fr in the rotor, then it will rise to f plus or minus 2 fr in stator. Okay. This is stator, rotor, stator, goes on continuing like that ad infinitum. Okay. So, there will be several such series of things will be there. In fact, we can represent like a circuit. So, you will have f here, you will have f minus fr, f plus fr, then it will come back to stator f minus 2 fr, f plus 2 fr. So, you have equivalent circuit which goes infinitely, okay, goes on continuously. So, you think about it, it requires introspection. Okay. Maybe you can get hold of this paper, read it before you come for the next lecture. So, we will understand it better. Is it okay? So, we will stop it here at this time.